All right, so we are going to continue with a review of the material to kind of get prepared for the final exam. Gonna do, I have 4 problems. We'll see how many we'll get to. So I have this one, and 2 of the 3D free body diagrams that we will work on. So let's just start with this one. The mass of the wing of a small plane is 27 kilogram applied at the centroid of the wing as shown. And the lift force on the wing is expressed as this much. Find the magnitude and location of resultant force from the lift force. And B, find the reaction at R, the support. Free body diagram is required. So this is a case of distributed load on a beam. The problem is asking me to find FR. Okay. And X bar, the location of the FR, which the problem kind of gives the centroid, but let's find it. Let's assume that this is not given. So in words, do you guys remember what is FR? Not the equation, just the word. What is FR when you have a distributed load?
FR is the total like area underneath loading.
So it's area under loading. Which in this case is going to be D area, which is going to be A, total A. What is X bar? Again, in words.
Distance to the centroid.
So it's distance to what?
The centroid of the area.
This is just centroid of the area, which is X tilde dA over dA. Okay. All right, so I got to find dA and I got to find X tilde. If I have this curve here, I'm going to take a little area, just the way we find centroid, Y, or I think we could have called this W. Let's call this W. And this is X. So this D area has W dx. X tilde is the distance of the centroid of this area to the y-axis, or in case w-axis, which is equal to x. So this one is going to be w dx, and this one is going to be x w dx over w dx. Okay, so now let's substitute and figure it out. So FR W dx equals, W is given by minus 300 2.4 x3 dx. What are the bounds of integral for this integration?
0 to 5.
0 to 5. So it goes back how much x is changing. X starts from 0 to 5. So this will result in minus 12 newtons. Why do I have minus? What does that mean?
It's going in the opposite direction of what is expected, I guess you could say. So generally,
Exactly.
you see it going down. So since it's minus, it's going up.
Exactly. So typically we have a load, most of the loads that we've had, they were pointing down, right? This one is going opposite of whatever we wanted. So in other case, I think this is minus W axis for some reason. This is minus W, this is plus X. That's what it is. Because look what happens if X equals to, so this is the equation, right? Minus 300 plus 2.4 x3. When X equal to 0, W turns out to be minus 300 pounds. So this point right here is minus 300. Again, it's just a math sign. It really doesn't make sense for our signs that we usually said, hey, this is always positive, right? This is always positive. But in this case, it's because it's a little bit of math involves. That's what the meaning of is. You want to see it gets more interesting because this is supposed to be area under loading, right? So how can an area be a negative number? Again, this is the area. This just says it's pointing up. That's it. Okay, otherwise area cannot be negative. So let's find a centroid. Let's see if the 2 that they give us was correct. So I have to do x minus 300 plus 2.4 x3 0 to 5 dx over this area, which is 1125. Okay, so if you do the integration, you're going to get minus 300 over 2x2 plus 2.4 over 5 x4 25 Newton. So this actually is going to be minus 2250 Newton meters minus 1125 Newtons. So that's going to give you x bar equals 2 meters. So it was given, I think if it wanted to be a little bit, oh, sorry. It wanted to be a little bit challenging, instead of giving that centroid, it could have said, hey, the weight is applied at the centroid. Now go find a centroid. So, which we already did. Okay. Questions? So it's important to, first of all, I hate to use the word memorize. It's more learn, okay? Don't memorize these. Learn them. That, hey, FR is the same as area under the load. And X bar is where the center of this area is. Once you do that, even if you totally forget these equations, just based on understanding them, you can figure it out and write the equation. If you are somewhere without internet, without Google, without your textbook or cell phone, and you have to figure out centroid of something, by just remembering what it means, you can come up with the equation. No need to memorize the equation. Questions about this so far? This was part A. Let's look back quick. Find the magnitude and location of resultant force, which we did. Find the reaction at R. We still have one more step to do. If there is no question, I'm going to wipe these off. Okay. I keep this bottom part up there in case someone is still writing them down. So what we have so far is this airplane, wing, whatever. Now what I have is this force of 1125 newtons at a distance of 2 meters. That's what I figured so far. I've simplified it. To do the support reaction, I need to draw a free body diagram of the wing. I'm only drawing free body diagram of the wing. So please, something to remember for your exam, when you're drawing free body diagram, write it and figure out what is it that you're drawing free body diagram of. I'm drawing of the wing, so I'm going to do isolate an outline of the wing. There. Okay. Next step is to put active forces. The active forces that I know is a 27 kilogram multiplied by 9.8 meter per square second. Now it's a force. And I just figure out that 1125 Newton pointing up. Those are my active forces. What about reactive forces? What kind of reactive forces do I have here?
Rx, Ry, and moment about R.
Okay, so what type of reaction is R? What, what kind of support is point R?
Fixed.
It's a fixed support, right? Thank you. Fixed means it does not move in X, does not move in Y, does not rotate about M. I better not, otherwise you don't want to get on that airplane, right? If the wing moves in X or Y or rotates. So it's 3 no's, that means 3 forces. 1 in X direction, 1 in Y direction, and some a moment. There we go. 3 equations, or sorry, 3 unknowns. I have 3 equations. Let's see, summation of forces in X being 0. Now I don't care about the math and this is negative axis. I'm just gonna have my own sign that I always had, right? Anything that points right, I'm gonna take it as positive. Rx plus nothing else, so Rx is 0. Which, when you think about it, it's a good thing for me. I don't want this airplane, probably, you want this airplane to move this way toward me out of the plane, right? You don't want it to have going left or right. Okay. Summation of forces in Y being 0. Again, I don't care about the signs of previous section that this was negative. Anything that points up, I'm going to take positive. So I have Ry plus 1125 minus 27 9.81 equals 0. This will give me Ry of minus 860.3. So this Ry is actually pointing down. Okay. The other thing, last equation that I have, summation of moment about point R being 0. Anything that rotates this way, I'm going to take positive. Taking it above point R, so Rx and Ry, they're 0. I still have an MR that I have it as negative based on what I drew here. Then I have an 1125 Newton multiplied by 2 meters, and that's going to create a rotation this way, so that's positive. I have a minus 27 9.81. I just keep it like this on purpose, so when you guys go back and review it, remember, hey, this is the weight that we have. Don't want to put a number and then you're going to forget that, hey, what was this one? Where did this come from? This one creates a moment this way, so that's negative, equals 0. This one will result in MR of being 1720.2. If I want to go by 3 sig figures, it's going to be 1.72 kilonewton per meter. Okay. Questions about this? Okay. So, by the way, one thing I want to mention here, just again, it's a little detail. Let's see. Is this the unit? Is this kilonewton or is this kilonewton? Is it 1 or is it 2?
1.
1. 1. Okay. So you got to pay attention. Kilo as a prefix is a small k. The reason I'm saying this because I've seen people using this in this class. Okay. What is problem with this? What if I write it like this? What does that mean? In other words, what is K? Capital letter K.
Degrees in Kelvin.
That's Kelvin, right? That's temperature. So pay attention to like little details even when you're writing. In other classes and whatever, just that shows that, hey, I understand this. And I know the difference, okay? Just pay attention to that little detail, all right? So before going on with the next problem, the I, there was a little section from my video that I want to I don't want to play the whole thing. I want to remind people to go back and watch it, all right? So this is a lecture on chapter 10, about 4 minutes in. The discussion is about the I and how we will use it in other engineering courses and classes and equations, and what is the difference between the areas and how we're using it, okay? So one thing that I discuss in this video is we're dealing with second moment of inertia. I think inertia is 1n, inertia. So if I want to make a meaning out of it, it's pretty much, if I have an area, okay, first moment of inertia would be YA. Okay, so this area multiplied by this distance. Again, just if I want to kind of make sense of it. Doesn't have any physical meaning, but as if it's an area, moment of an area about an axis. So it's going to be YA. The second moment of inertia, as we use it, it's going to be Y2 area. Okay, and that's why it has, I has units of inch for, or feet for, or meters for. Okay. In this part of the video, I explained that, hey, I deals with the stresses and all of that. And it usually shows up in denominator of equations, right? So we have, for example, a stress in a beam is MC over I. So the bigger the I is for that area, just you have less stresses, okay? And that's why I talk about this. This is better than this one, but then a beam like this one, like the last one, is even better than the previous one because you're putting more area away from the axis, okay? But then the next part of it, it goes even further to talk about a technique that's pretty much, it's used a lot in structural design and in buildings. And that's when you have an I-beam like this, okay? It already, we talked about that. This is a good So this is, I'm drawing the cross section of it. This is pretty good because you're putting a lot of area away from the neutral axis. Okay. But then by using a technique which they cut it like this, kind of like a honeycomb pattern, and then you lift the two pieces, you move it over, so you weld this part to this part to this part, and so on. You create a beam that's like this. So some of you might have seen this a lot in different buildings, especially in tall buildings that are steel structure. You see that pattern a lot. The reason is this beam has the same area, okay, and has the same cross section and everything, has the same mass. But now look, when you compare these two together, you have even put this area even further from the neutral axis. So you are increasing this y squared part of it. So your I is increased by a lot. So it's the same beam, but you are getting a lot out of it by just messing around with that I number, which is, again, we said it's a property of the area, property of the cross section. So this will be the use, especially for civil engineers who are taking this class. This will be a big part of what you got to use in a structural design, is calculating the I for different cross sections and different materials. I go back and talk. So these are very interesting stuff if you want to. These are something that's not part of your lecture. I think the lecture starts from somewhere 8 minutes into it that we generate. But if you haven't watched the lecture video, please watch that 6-7 minutes at the beginning of it. It's kind of interesting. Okay, so now let's get to this and try to find the I. So okay, now aluminum extrusion is being designed as shown. Find the centroid of the area above x-axis. This should have been like big X. And the area moment of inertia about x-axis. So pretty much find this y bar and moment of inertia about x-axis. So let's take this to the whiteboard here. All right. So let's just start with the easy one, which is the y bar, because we just did one, so you guys kind of remember it better. Y bar is y tilde dA over dA. So I have to take an area moment, and I told you, do not draw it on the shape. Just take a minute. Draw it like this. So I'm going to take a little sliver of area. Okay, so this is my dA, which is this length here, which is y, and it is dx. And y tilde in this case is going to be what? What is y tilde?
Y over 2.
Okay, y over 2. What else? So first of all, what is y tilde in words?
Distance between the x-axis and the centroid of the sliver.
So x-axis and centroid of dA, that's sliver. Okay. Someone said it's y over 2. What else? It's not right. So I tell you what. Because this is not y. This is something else. But what is it? So this entire length is not y. You have to figure out what it is. Or just give me a second. Okay, maybe I was, because I was thinking this point here is y plus 1. Y plus 1. Let's see. If x equals 0, then your y is 1. No, this works. This is y, and you're correct. This is y over 2. So never mind. Scratch that. I was thinking this is y plus 1, but it's not. It's just y. Okay, so we got our x tilde and y. So it's going to be y over 2 y dx over y dx. So I got to figure out what is my x. So y equals 1 plus this. So y minus 1 equals x. So y minus 1 squared equal x. All right. So, or it's better to do it y equals 1. You know what? We need this for the next part. We don't need it for this part. All I have to do is just replace the x. Never mind. Totally lost my focus on this one. So 1 plus x over 2. Okay, now this makes sense. 1 plus x over 2 dx. There we go. And 1 plus x dx. Does that make sense? Is that correct? And the x is going to move from 0 to 1, 0 to 1. Colton, does that make sense to you? Did I miss anything?
I don't believe so.
Okay. So I haven't done the final answer, but the solution, I have it right here, is not correct either. So I don't have the final answer for this. Any questions about part 1? That was just y bar. Okay, let's do the I x. The integral is opposite, right? So, and I'm gonna draw another sliver of your area. Yx. So which way should my sliver be? Parallel to x or parallel to y?
Parallel to x.
Parallel to x. Okay. Someone asked for me to use the rainbow pen. So parallel to x. Okay. So I'm gonna take an area here. Little tiny sliver. This is actually pretty cool. This is going to be dy, and this is going to be just 1 inch. So similar to the one that we did before, I have to divide this into 2 areas. Remember that? Because look, my area, the sliver of area is not changing from 0 all the way to y equal 1. Okay? It's not changing. My dA is going to be 1 inch dy. That's it. So I'm going to have the 2 integral as before. From 0 to 1, I'm going to use this dA. So it's going to be y2 dy. And then for the second part, I'm going to use its other dA. So it's going to be dy. What is this dA going to be? What is this length here?
One minus x.
That one is 1 minus x, exactly. Let's get rid of this top part. Okay. There we go. Hey, there's another one that is a galaxy pencil. Let's see that one. Cool. It's really cool. Okay. This area here that I'm trying to find, dy, this length here is 1 inch. This point is x, okay, if it's exactly at the point. So this length here is going to be 1 minus x, okay? So my second integral, which is going from 1 to 2, is going to be this one now. 1 minus x dy. Is everyone following, or is everyone distracted by the colors? Okay, so the last thing I want to do is just find x and replace it, because I have dy, everything needs to be in x. So let's see, y, 1 plus x over half, 1 minus 1 equals x to the power of half, 1, y minus 1 equals x. So if I replace this here, then I have my integration done and ready. y2 1 minus x. So 1 minus y minus 1 over 2 dy. It looks a little bit scary, but once you do it, it's not, doesn't look as scary as it should be, okay? All right, you do the math on this one. I'm gonna write it. These are so pretty, I don't want to delete it, but I'm gonna write it for people in black so they don't get distracted. 0 to 1, y2 dy, 1 to 2, y2 dy. This is going to be your ix. Okay? Questions? I think you should be able to set the, yeah, I think you can pick what colors be included in the rainbow too. That's pretty cool. All right, questions? Okay, I think we've done enough on central as a moment of inertia and all of that, and hopefully everybody has a good understanding of at least what to do. If you make mistakes here in DA and stuff like that, that's totally fine. Everybody makes mistakes. The important is that you understand what you're doing. You're not just writing stuff in the dark or just plugging numbers in these equations. That's what you got to learn from this class. But everybody makes math mistakes here and there, which is fine. And I don't really care about those as much, okay? All right, I think it's enough with central and all of that. So let's go back to some of the older material that you guys, and we'll see how much you remember. Okay. The contraption shown is intended to provide a normal clamping force at point D. Okay, a normal clamping force at point D. Something like this. This is a normal force perpendicular to that surface. The spring is used to, is a stretch 30 millimeters. Okay, so it's already stretched because it's keeping this down. In the position shown, calculate the force P, where is P? Right here, needed to release the clamp. Find the radial forces on two bearings at B and C. When it is applied, B and C are in proper alignment. All right. So there, before we start solving and drawing free body diagram and stuff, let's figure some stuff out. First of all, let's focus on what it means. Calculate the force P needed to release the clamp. This is a super important word for us. What does that mean? Right now, this spring is stretched, right? So there's a clamping normal force here. We can call it FD or ND. You want to start applying force P for this clamping force to release. What does that mean?
The normal force is 0.
That means it's not going to move, but you want to find that P that releases this, right? When it's released, in other words, when it's not contacting the surface or applying any load, that means this is going to be 0. So it could have just said, find the P for the clamping force to be 0. That's one important piece of information. Another important piece of information is, it says radial forces on the two bearing at B and C, the B and C are in proper alignment. Let's see who remembers what does that mean for us. What does proper alignment? So proper alignment means there is no unbalance what on them. So let's go step by step. That means no unbalanced what?
It's not like a moment.
Moment. Great. No unbalanced moment. So if there is no unbalanced moment, what does that mean for these two bearings? Step 2.
They don't cause a moment.
So there is no reactive or reaction moment on B or C. That's the meaning of proper alignment. Okay, this is the way you can think about it. If you put a table, okay, so something like this. If you put a table on the floor, we'll only look at it 2D, and it has, let's say, 100 pounds. Okay, because there's 100 pounds pushing down, and let's say, so it means 25 pounds pushing down on each leg. There is unbalanced 25 pounds on each leg. Therefore, the ground or the floor is going to create 25 pounds to balance this. As a result, the floor is going to have 25 pounds reaction, the normal force. Okay. So now I'm going to say proper alignment. Okay, let me see if I can erase the floor. Now I say this table is, by some mechanism or whatever, is hanging about 2 inches off the floor. So it's not even touching, 2 inches. So that, then in this case, there is no unbalanced 25 pounds at each leg, right? As far as floor is concerned, floor is like, I don't feel anything. So the floor is not going to have those 25-pound forces that we had before. See what I'm saying? There's not going to be a force because there is no active force, there is no reactive force, there's no action, there's no reaction. Same thing here. When it says proper alignment, means there is no unbalanced moment. There is no action, therefore there is no reaction needed from the bearings. So that's the meaning of proper alignment. Means there's no unbalanced moment. But in case some unbalanced moment happens, some person start kicking this device in this direction, right? Then I can see that there would be some unbalanced moment in this direction. So therefore, they're not in proper alignment. But as it is right now, there is no unbalanced moment, so we don't have to worry about it. So let me draw. I know this is not exactly the way we tell you to do it. We tell you to draw, isolate and draw. But this problem, because this was too much, it gives an give a figure and said, hey, try to draw forces on this one. Okay. I know this is, again, not the way we say isolate means remove all of these, but we're just going to follow the problem. So we're just going to put forces on here. Okay. And I'm just going to call it not FBD to just be correct. All right. Force P is applied. I'm going to put an FD here. So I know there's a clamping force, but I'm going to just make it equal to 0. So bearing C and bearing B, I have only axial forces, no moment. So I'm going to have CY and I'm going to have CX. By the way, this XYZ was just like this. This was X, this was Y, and this one was Z. B, same way. I'm going to put a BY and I'm going to put a BZ. No moment.
You have two CYs on the C.
Oh, yes, CY. One of them needs to be CZ. This is CZ. Thank you. And then last thing I have is force of a spring. And that's it. And this is my free body diagram. So if you want to draw a proper free body diagram, should be something probably like this. I'm just going to draw it really quick here. Okay. So you can call this one FBD. So B, Z, BY, FS, CY, CZ, FD, and P. We can call this one FBD. Okay. Questions about free body diagram on this one? I mean, this is the most complicated 3D free body diagram we can have because it has a clamping force, it has an active force, it has a spring on it, it has 2 bearings on it. But if you follow the steps, the 3 steps, isolate, active, reactive, you should be fine. Okay. One equation, and you are able to find force P. One equation. That's all you need.
Summation of forces in the z direction.
Summation of forces in z direction. I have too many unknowns. I have BZ and
Oh wait, yeah,
CZ.
never mind. I see it.
Yeah.
Moment about x-axis.
Moment about x-axis, exactly. So this is x-axis. So if I take summation of moment about x-axis equals 0, as if it's like this. This is my x-axis. X, well, let's just do it this way. X. I have a force P that is pointing up at a distance of 135 mm. And I have force of a spring that is at a 45 mm. So all I have to do is say P 135 should be equal the force of a spring, which force of a spring is going to be 900 Newton per meter, 30 millimeters displacement is going to be 27 Newtons. This is all given. It's going to be 27 Newtons by 45 mm. And you can find P of 9 Newtons. Again, this is a force that will result in FD being 0. This result in FD being 0, or that release of the clamp. Okay, so we can go over the rest of it to find BZ those, but those are pretty easy. I can give you the equation. You can take moment about axis Z at point B equals 0, and then take summation of moment about Y, point B is 0, and after that just summation of Fy and Fx, and you can find all other the other 4 unknowns. These are the 4 equations you want. Okay, questions? Any questions? All right, so the last thing I want to mention before I let you guys go is just kind of a reminder of the exam. So now, based on the feedback I got, if you said yes and you want to, and you still, you know, haven't changed your mind, final exam is going to be next Wednesday, which is 5th. May 5th, 2 to 3 p.m. If you said no, or you don't want to, you don't like this, that is totally fine. Final exam as scheduled before. It's going to be May, is that 13th or 12th?
12.
12th, yes. 3:30 to 4:30. Again, both exams are going to have the same, not same questions, but same level of difficulty. They're both 1 hour exam, and they both cover the entire statics. Kind of, it's not going to be anything harder than any of the review problems I did, I promise. So if you go over the review problems and I understand them, you're 100% good for the final exam. So this is it. So we're going to have Monday for review, and that's it. That concludes our statics. All right. But I'm going to remind you of this Monday too. I've got some emails from students. I think 3 emails that I haven't had a chance to respond to it yesterday and the day before. I'll get to those. I've got your emails about gradings and Blackboard and questions. I'll get to those for sure. Otherwise, guys, good to go. Have a good weekend. And I'll see you Monday.